crystal field splitting. While discussing quantum theory of paramagnetism, we introduced a factor called effective magneton number P equal to G into root of J into J plus 1 the whole raised to half. Here we defined while discussing susceptibility of paramagnetic substance, we introduced P equal to G into J plus 1 the whole raised to half. This was defined as effective number of Bohr magnetons. In case of lanthanide group ions, they are also paramagnetic. These ions are examples are Ce3 plus, Pr3 plus, Er3 plus, erbium3 plus, Yb3 plus, etc. In these ions, lanthanide group ions, which are paramagnetic, this value of G into root of J into J plus 1 equals the experimentally determined magneton number. But in some cases of paramagnetic materials like iron group ions Ti3 plus, V3, V4 plus, vanadium 3 plus, CO2 plus, Fe2 plus, Cu2 plus, etc. The experimental value of magneton number is not equal to our definition, but it is equal to 2 into root of S into S plus 1. S is the spin quantum number while J is the total angular momentum quantum number of the atom. The difference between these two ions, first one is rare earth ions like lanthanide group ions and other is iron group ions. Let us see what about lanthanide group ions. Example is Ce3 plus. Its outer electronic configuration is given by 4f1 5s2 3p6. We know the filling of orbitals is according to this rule. First 1s is filled, then 2s, then 2p, then 3s, then again 3p, 4s, 3d, 4p, 5s. This is the order of filling of different orbitals. In the case of Ce3 plus, the configuration is given by this, and the term symbol, we can find out term symbol for the Ce3 plus ion. It is 2f 5 by 2. The electron in the 4f shell is responsible for its paramagnetic behavior. And in this case, lanthanide ions, calculated value of P from equation G into root of J into J plus 1 is equal to 2.54, and experimentally determined value of P, effective number of magneton, is nearly equal to this calculated value, equal to 2.4. Next example is an example from iron group element ions, that is Fe2 plus. In this case, the electron configuration is 3d6 and term symbol is 5d4. Here we can calculate P by this equation G multiplied with root of J into J plus 1, and it is found that it is equal to 6.7, and experimentally determined value of this P is 5.4, which is different from the calculated value. But when we calculate 2 into root of S into S plus 1, it is nearly equal, 4.9. Therefore, the value of P agrees more with 2 into root of S into S plus 1. The difference between these two ions, like lanthanide rare earth ions and iron group ions, is that in rare earth ion, 4f shell is responsible for the paramagnetic behavior and it lies within 5s and 5p shells. It is an inner shell. But in the iron group ions, 3D shell, electron in 3D shell is responsible for paramagnetic behavior. And this 3D shell is outermost shell. 3D shell, electron in 3D shell is the responsible for paramagnetic behavior and it is outer shell. Therefore, it experiences influence of an inhomogeneous electric field produced by the neighboring ions. This inhomogeneous electric field produced by neighboring ion is called crystal field. Therefore, in ion group ions, the electron responsible for paramagnetism is in 3D shell and this will experience a crystal field from the other neighboring ions. The interaction of paramagnetic ion with crystal field will have two major effects. First one is the coupling between the two vectors, that is angular momentum, orbital angular momentum vector and spin angular momentum vector is broken. They will not give a resultant J value. So the states are not specified by J value. Therefore, we cannot calculate the effective number of magneton using the equation of root of J into J plus 1. Next major effect is that for a given L, there will be 2L plus 1 sublevels in presence of crystal field. L level was degenerate in absence of this crystal field, but in presence of field this is split into 2L plus 1 sublevels and this splitting is called crystal field splitting. This type of splitting will diminish contribution of orbital motion to the magnetic moment. Thus, this is about crystal field splitting. Next topic is cooling due to adiabatic demagnetization. We can produce very low temperatures by demagnetization process. About 10 raised to minus 3 Kelvin can be achieved using this method. At a fixed temperature, the entropy of system of magnetic moments is lowered by application of magnetic field. This is an external applied field. When this field is applied in the paramagnetic material, the magnetic moments get aligned in the direction of external field. Thus, the disorder of the system is decreased. That is, entropy is reduced. Entropy is measure of disorder of the system. Greater the disorder, higher is entropy. In magnetic field, the moments are partly aligned, so entropy is lowered by the field as shown in the diagram. Entropy can be lowered by lowering temperature also. When temperature is lowered, the system will become more ordered and entropy is reduced. If magnetic field is then removed in this low entropy state without changing the entropy or spin of the system, order of spin system looks like low temperature system. That is, magnetic field is removed in an adiabatic condition. Adiabatic means there is no change in heat. Heat is not entered into the system or left from the system. That is, dq is 0. This means change in entropy is 0 or entropy remains constant in this adiabatic process where now we are removing the external applied field. When specimen is demagnetized at this constant entropy dq0, adiabatic condition, entropy will flow into the spin system from system of lattice vibration. It is the same system where energy is distributed in spin and lattice vibrations. When field is removed, the um, magnetic moments start disorienting while it requires energy and it is taken from system lattice vibrations. At low temperature, entropy of lattice vibration is also very small. This entropy of the system is constant during adiabatic demagnetization. Entropy of spin system can be calculated from the following procedure. Let there be n ions having each of spin s. A temperature sufficiently high that spins are disordered, that is T is very much greater than delta, and delta characterizes energy interaction tending to orient the spin change. Entropy sigma of system with G states is given by sigma equal to K log G, where G is the number of states available. There are 2s plus 1 possible states for one ion. Therefore, for n ions, there are total number of states available is 2s plus 1 raised to n. And spin entropy can be given as sigma equal to k log omega, that is log of 2s plus 1 raised to n. 2s plus 1 raised to n is the number of available states for the system. And this is equal to nk log 2s plus 1. This is the entropy of a spin system having n number of ions or spin ions. Now, let us discuss the steps carried out during this cooling adiabatic demagnetization cooling process. The field is applied at a T1 Kelvin. T1 Kelvin is also low temperature, and at this temperature we are applying field with the specimen in good thermal contact with the surrounding, giving isothermal path. In the figure, AB shows the process. System is in thermal contact with its surroundings, and we are applying a field 100 goes. Then the magnetic moments will get aligned. This process is given by AB. The y-axis shows in this diagram, y-axis shows entropy in nkb and the units of nkb, and x-axis shows temperature. This AB is a process taking place at a higher temperature, which is also in millikelvin range, T1 Kelvin. When temperature at constant temperature, entropy is reduced. By applying field, the ions get ordered. Next, specimen is then insulated from the surroundings. Now the surroundings dq becomes 0 because the system is insulated from the surrounding. When dq is 0, change in entropy is also 0, that is entropy is constant, and the field is now removed. When field is removed, the specimen takes a path, follows constant entropy path BC as shown in the figure BC. This is temperature is reducing to another T2 Kelvin, but entropy remains constant in this process. Field is reduced, field becomes lower, and the entropy increase in entropy due to this disorientation is taken from the vibrational energy. Therefore, temperature reduces to T2 Kelvin, and a path is given in the figure T2 Kelvin. Thermal contact at T1 is provided by helium gas, and contact is removed by removing gas pump. Therefore, in this process we can reduce from T1 Kelvin to about T2 Kelvin by this adiabatic demagnetization. This is a demagnetization process. First we apply a field and then we remove the field. Thus, it is a demagnetization process in which temperature is reduced from T1 to T2 Kelvin. Next is nuclear demagnetization. In addition to electronic moments, there are nuclear magnetism also, nuclear moments also due to nuclear spin. Cooling can also be achieved by demagnetization of these nuclear paramagnets. Population of a magnetic sublevel is function of B by T, where B is the magnetic flux and T is the temperature. By MB statistics, also Maxwell-Boltzmann statistics, N is number of our population in a state is proportional to exponential mu B by Kt, that is B by T. Then hence entropy is also a function of B by T, since spin entropy is function of population distributed. Therefore, entropy is function of B by T. Let B delta be the effective field corresponding to local interactions that is required for transfer from one state to another, and T2 be the final temperature achieved in adiabatic demagnetization. Adiabatic means entropy remains constant. Then the equation of entropy same in the final and initial state is B delta by T2 equal to B by T1, where B and T1 are the initial field and temperature. Therefore, final temperature obtained is equal to by demagnetization is B delta by B into T1. B is small since nuclear magnetic moments are very weak. In this case, we can reach up to 100 times lower temperature with the nuclear paramagnet than with the previously discussed electronic paramagnet. If T1 is 0.01 Kelvin and B is 50 kilogauss, then B delta equal to 3.1 gauss, then resultant T2 will be equal to about 10 raised to minus 7 Kelvin, that is very low temperature.